Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing a crash course on the topic of kinematics for Cambridge AS Physics 9702. Now, this is one of the first few topics that you'll encounter when you start A-level physics, your first year of A-level physics, and it may be familiar to you, but we cover it in a good amount of detail, and we actually use it throughout our A-level journey. And so whenever we solve problems in physics, in A-level physics, we should at least have an idea of what kinematics is and how to apply it to solve bigger problems, and what the use of it is in the bigger picture. So in this crash course, we're just going to go over the most important concepts and the most important ideas, just to give you a brief summary of what is contained in this topic. But we always, or should always, start with the most basic definition for the physical quantity that we usually learn first, and that's distance, and the vector equivalent of distance. And so what we know is that distance is a physical quantity, and we can define distance, again, you can find this in your textbook anywhere, as the length along the path moved by a particle from start point to end point, and distance is a scalar quantity. So it's a physical quantity and it is a scalar quantity. So don't think this is really going to trouble you, but distance is basically how far you move when you go somewhere. So if I look at the entire path that you take from start to finish, we'll do a little example now. If I take the entire path and I measure the length of the entire path, then what I have is your distance. So if the path is zigzag, if it's jagged, if you're back and forth, irrespective, I measure the entire length that you have walked. But then there's a vector equivalent to distance called displacement. And these two are not necessarily always the same. The displacement is the straight line length, and again we'll see what this means, the straight line length in a specific direction, again from start point to end point. But because I said it must be in a specific direction, displacement is a vector quantity. So a vector quantity is any quantity that has magnitude and direction. So distance only has a magnitude. It is measured in meters. The SI unit for distance is meters. The SI unit for displacement is also the meter, but it also requires a direction. So let's look at an example. So let's consider our cardinal points as we usually would. Up being north, and then our other three cardinal points. Never eat silkworms is how I remember them. North, east, south, and west. And so if I consider these as my directions, and I need direction for describing vectors, then let's assume that one day you decide to take a walk and you start at point A and you walk north to point B, and then from point B you walked eastwards to point C. Again, my diagram is not going to be completely accurate, but let's say you walked a distance of 300 meters from A to B, you went to visit another friend, and that from that friend's house, from B to C, you went to visit another friend, and that distance was, let's say, 400 meters. You can obviously see where I'm going with this. And if I were to draw a line from start point to end point, I started at home A, but I ended at my second friend's home, which is labeled C, and the angle between AB and AC, I'm going to call it theta, just to give it some reference. And that's obviously 90 degrees. So I walked northwards and then I walked eastwards, just for simplicity's sake. So why am I doing this? Because the distance that was traveled would be 300. I'm just going to write it down as distance is equal to 300 meters plus 400 meters. So the total length of the path that I traveled was 700 meters. So I physically moved 700 meters. So I physically exerted myself over 700 meters. My displacement, on the other hand, is going to be a little bit more tricky. So my displacement, I can see, will require a bit of Pythagoras. I have a right angle triangle, and I'm trying to find the hypotenuse of this right angle triangle. And so it is the square root of 300 squared plus 400 squared. Now you see why I chose these numbers. So the displacement is 500 meters. So AC was 500 meters. So in actual fact, my displacement is only 500 meters, even though I physically walked 700 meters. But displacement also requires an angle, or requires a direction rather. So in this case, I'm going to use my angle to describe the direction. So I'm going to find what theta is. Now, with a little bit of mathematics, and not really complicated mathematics, I can see that the tan of y over x, the tan of north over east, if you would give me the angle theta. Or rather, the tan of theta would be y over x. So theta is the arctan of the y component, or the vertical component, actually it's the other way around. It's in this case, so tan is opposite over adjacent, opposite to theta is 400, so it's 400, the horizontal distance, divided by the vertical distance as we look at it, 300, which is the adjacent side to the angle theta. And what I find is the angle theta is 53 degrees. So it's 53 degrees as I've drawn it, but whenever I want to state a vector, it's always good to write both the magnitude and direction together. So what I would say is displacement is 500 meters, and then I'm going to say 53 degrees, but that's not useful unless I have the diagram in front of me. So to make it useful for anyone reading this value, I would say 53 degrees east of north, or E of n for short. 53 degrees east of the north line, which is AB. So that's my actual displacement. I need the magnitude and I need the direction. That's how I specify my displacement. So that's distance and displacement. Again, I don't think those are really complicated definitions, complicated quantities to understand, but it's important that you understand that there is a difference. And if a question manipulates the difference between those two, then you have to be prepared for any complications from the subtle differences between those two quantities. Now, the other two quantities that we require, well, the two base quantities that we require are average speed. In fact, we'll just write this down in pen. We require average speed and average velocity, or speed and velocity, two new quantities. Well, we say new, but they kind of will have been familiar to you from the time you would have started learning about science in any form. But average speed, or speed in general, is the rate at which distance is changing. Please remember, do not say it's the rate of change of distance with time, because the rate of change in itself implies something divided by time. Okay, and so if it's a meter divided by a second, it is measured in meters per second. If anything in this crash course is feeling a bit unfamiliar, my suggestion would be to just maybe look at something done in IGCSE, in a textbook from IGCSE, on the topic of equations of motion, or on the topic of kinematics, or motion in general. But average speed is distance over time, measured in meters per second. Okay. But what about velocity? So velocity, if I was speaking English, would sound roughly the same as me using the word speed. But in physics, it has a different meaning. It's also measured in meters per second, but you guessed it, it is now a vector quantity, so it's displacement against time. And so it has an inherent direction associated with it. And so the average velocity, we use a bar above the symbol for the quantity, and we use v for velocity, hence I'm using the symbol v, as my position x2 minus my position x1. If let's first write what I'm actually referring to here. Let's assume I'm walking on a straight line, and I start at position x1 on the straight line. I go for a bit of a walk, and I end at position x2 on the straight line. And all this time I was walking east, so everything to the right is positive. And after time t1, I reached x1, and after time t2, I reached x2. So my average velocity is my change in position, the displacement that I've covered, divided by the change in time, t2 minus t1. And so that is how we define velocity. And we also sometimes say that this is delta x by delta t. The Greek letter delta stands for change. Change in displacement over change in time. Change in position over change in time. And it's a vector, so it's good to say the magnitude is x2 minus x1 over t2 minus t1, but the direction here is to the right, and we usually stick to the convention that the right is positive because our number line to the right is positive. But again, it's just a convention, and we can assume whatever convention we deem necessary depending on the problem that we're working with. Now, that's average speed and average velocity. And then the last quantity, the last introduction that we're going to do is that of something that I'm more than likely going to be reintroducing rather than introducing, average acceleration. So the average acceleration is how rapidly your velocity is changing. How many meters per second is your velocity changing every second? So it's change in velocity divided by change in time. And you guessed it, this will be given the symbol A, and it's delta V by delta T. So if I'm speeding up or if I'm slowing down, I say I'm accelerating. We sometimes say decelerating if you're slowing down, but the word acceleration is fine. And obviously I can see that I have a meter per second divided by a second. So this is measured in meters per square second, which is equivalent to meters per second per second. Kind of makes sense, right? How many meters per second is my speed changing every second, right? And that's my average acceleration. Why do I say average? The same reason I say average speed and average velocity. It's because I said average velocity is displacement over time. But I didn't say that when I walked from x1 to x2 that I was walking at a constant rate. I could have stopped to smell the roses and then picked up my pace over the last millisecond. So we can only assume that my average velocity was my displacement divided by my time. But on average, that's, again, just a single value. I could have been moving slower than that at some point and then faster than that at some point. And it averages out to be that value v. So this is why we specifically said average. It's the same for acceleration. My velocity can change at any rate at any different point in time. but on average, over a period of time, it's the final velocity minus my initial velocity divided by the time. So remember, this is why we use the word average rather than just saying speed and velocity. Now, for uniform motion, and I'll discuss what uniform motion means, we have a set of equations, and we call them the kinematic equations of motion. Now, why do we use the word kinematic? And where does the word kinematics come from? Well, kinematics simply means the study of motion, but specifically in physics, it is the study of motion when we don't really care what's causing the motion. We haven't, and we will not in this topic, discuss where motion is coming from. We're not going to talk about pushes or pulls or forces or torques or any of those things. We just really care about if something is moving, how is its motion going to change, or how can its motion be described rather. And so if we have uniform motion, so if A is uniform acceleration rather, I should say, if the acceleration is uniform, what this means is the value for the acceleration is constant. Acceleration is not increasing and decreasing and fluctuating, it is remaining constant. Then you can use the four equations which you spent a long time memorizing. V is equal to U plus AT, S is equal to UT plus a half AT squared. And I'm not going to derive these equations. I mean, you would have done these derivations again and again. You can derive them if you wish. Two of them are given on your formula sheet anyway. V squared is equal to U squared plus 2AS, and S is equal to UT plus a half AT squared. So if I have uniform acceleration for any object undergoing uniform acceleration, I can use any one of these equations to find any of the unknown quantities about it, where V is its final velocity. What is the final velocity of an object after time t has passed? And U is what we call initial velocity. Again, this is just all convention. And so these are the symbols that we use. U is the initial velocity before the time t has passed. A is the acceleration of the object, which again must be constant, so it must be one number. And S here is displacement. And so these are called the kinematic equations of motion. Like I say, if you want to derive them, feel free to knock yourself out, but I'm not going to do that. I think I'm going to spend more time in this video discussing what the graphs look like, because I feel that's where I think the complications come in, and when we have to represent the graphs for two-dimensional motion. But the last thing I do want to say here is that for an object in free fall, that's an object falling through in the Earth's gravitational field, neglecting the air resistance, its acceleration is g, which is the acceleration of free fall, which is a constant 9.81 meters per square second. So for any object in free fall, A is constant. I want you to remember that it doesn't change. It doesn't matter if the object is moving up or down, etc. If it's in the Earth's gravitational field, it'll feel an acceleration downward and will accelerate with 9.81 meters per square second. Okay, so I think moving on to, for me, I think would be the most important part of kinematics. I think problem solving is extremely important. How to go about problem solving, but I think that would make this crash course a bit too long. If you want to, at some point, I'd probably put up a video on how to solve problems and going over past paper problems on kinematics. But for now, I'm just trying to cover all the theoretical and conceptual understandings. So let's first look at what the graph for a stationary object would look like. So I'm going to draw graphs of the quantity against time for different scenarios, for different types of motion for a specific object. And we'll see what the graphs of time for the different quantities, displacement, velocity, and acceleration look like. And so the first one will look as follows. So a stationary object, an object that is not moving, this is what we mean by stationary. If I were to sketch a graph of displacement against time, you've seen I've drawn positive and negative axes for displacement. I'm going to assume that that the preferred direction is positive, just for now at least. And we'll talk about what happens when vectors change signs and so on later on. But if an object is stationary, its displacement's not changing. And so its graph of displacement against time will just be a straight horizontal line. Why is it a straight horizontal line? Because x is constant. Just be wary that we are plotting x on the y-axis here, on the vertical axis, and time on the horizontal. Time is always our independent variable. And so x is constant for an object that's moving. So instead of it being a point on the graph, it would be a line on the graph, because at any time I can measure the displacement to be constant. And what about if I now talk about the velocity time graph for the same object? So I'm going to draw the velocity time graph for the object that isn't moving. Now we said velocity is the rate of change of displacement, so delta x by delta t. But there is no delta x, there's no change in my position. So I cannot be having a velocity. And so my velocity will be 0. So for the same time as I've indicated above, what I would have is I would have a graph that is just 0 all the way up until that point t. So I may not be able to see it, but it would just lie along the time axis, because the velocity is neither in one direction nor is it in the other. It's absolutely 0, so it will be 0 velocity. And it's also, if you know a little bit of calculus, it's the gradient of the graph of x versus t. So the gradient of a displacement time graph gives you the velocity. And then lastly, what's left, our last quantity that we want to plot against time will be the acceleration. The acceleration is given by how my velocity is changing. Is my velocity changing? It's not. So the acceleration is 0. Acceleration is the gradient, is given by the gradient of the graph of velocity versus time. There isn't a gradient for my graph of velocity versus time, so there isn't an acceleration. It's a flat line which doesn't have a gradient, has a 0 gradient. And so at any time the gradient is 0, and so at any time I plot an acceleration of 0. And so fairly straightforward, and this is for a stationary object. But what happens if I change the scenario just slightly and make it such that the object is moving, but with constant velocity? So I have some particle, some object moving with a constant velocity. So now I'm going to sketch the graphs that I've done so before. I'm going to sketch them again. But obviously they're going to look slightly different now. So what I will have is I'm going to say that maybe it starts at displacement equals to 0, and then it moves away from displacement equals to 0, and the time again is on the horizontal axis. So I'm going to say that at a time I'm going to call it T1. It had a position x1, and then this object continued to move at a time T2. Its position was x2. Now, how do I know it has constant velocity? It's because the rate at which the displacement is changing, which is the velocity, is constant. The gradient of this graph is a constant value. It's not perfectly drawn, but believe it or not, this is a straight line. And so this represents the displacement versus time for an object moving with constant velocity. Again, I'm assuming that the constant velocity is positive. I'm choosing the positive direction. I'm walking to the right with a constant velocity, or walking to the right with a constant speed. And what does this mean for the velocity versus time graph? Well, as it did for displacement versus time, if my velocity is constant, and then I draw a graph or sketch a graph of velocity versus time, it's just going to be a straight horizontal line. It's not changing. And whether I'm at time t1 or whether I'm at time t2, my velocity just remains some value v. Okay, so what we say here is that v is constant, the velocity is constant. Now be very wary, it may look, if you look at a velocity time graph that is constant, like the object is stationary, but it's not. It's just moving at constant velocity. Every moment in time it's getting further from where it was in the previous moment in time. And remember, v is delta x by delta t, and we can get it, like we said, by getting the gradient of the graph of x versus t, the graph of displacement versus time. The graph of displacement versus time has a constant gradient, whatever that number may be, and so the values of v against t will always be a constant number. It'll be equal to the gradient of the graph of x versus t. And I can also use, now the reason why I've labeled my points x1 and x2 and t1 and t2 is because if I wanted the displacement, that is covered by this object between times t1 and t2, then the displacement is the area under the vt graph, or the area between the velocity and the time axis between times t1 and t2, which means that x2 minus x1, which is the distance I would cover if I were walking from x1 to x2, is equal to the constant velocity v. I'm looking for this area, the shaded area. That's v into t2 minus t1, the area of that rectangle, the shaded area, which we know to be true. If I'm moving at constant velocity, then distance is speed times time, which is what this is telling me. So I can use the velocity time graph to find the displacement, which is quite powerful. And we'll see later on that I can also use it to find the acceleration. So I can use the displacement, the velocity time graph, to uncover quite a few things about the motion of a system. And so lastly, I need to plot a graph of acceleration against time. And so if I sketch acceleration against time, what I know is the acceleration is the rate at which velocity is changing, but velocity is not changing. So acceleration will always be zero for an object that's velocity is not changing. And it is the gradient of v versus t. So like I said, the v versus t graph, we can use the gradient to find acceleration and use the area to find displacement. So it's quite an important graph for us. There's quite a few uses for this graph. And if I'm moving at constant velocity, I will never have an acceleration. I can't be speeding up or slowing down if my speed isn't changing. And this is what this is telling us. Okay, so that's also all well and good. But what about the case where an object is moving with uniform acceleration, which will be the most important case for us, where we have uniform acceleration. So for an object moving with and I'm also going to specify that it's moving from rest, just to simplify the matter even further, but it's an object that starts at rest, starts stationary, and then starts accelerating uniformly, meaning its acceleration is constant. So first we had displacement constant, then we had velocity constant, now we have acceleration constant, uniform. And so if I were to sketch a graph of displacement against time, what I would find is that I don't have a constant velocity because I'm accelerating. So the rate at which my graph of displacement versus time is changing is not constant because v is not constant. So it's not going to be a straight line, but it's actually going to be some kind of exponential function. And it's going to be exponentially increasing if the object is accelerating rather than decelerating. Okay, so I'm going to take two random points on this graph, and we'll see why now. So I get a curve that is pointing upwards. It increases to the right, increases with the time. Obviously, I mean, if you start from rest and you accelerate, you're doing a meter per second after 1 second, but if your acceleration is 1 meter per square second, then in every second your velocity is increasing by a meter per second. So after 2 seconds, it'll be 2 meters per second, and then be 4, and then so it'll constantly, or 3 rather, and then it will constantly increase. So you're going faster and faster, and you're going to be moving away from your starting point faster for every time interval. So what will our graph of velocity against time look like? Again, this might be stuff that you are not really troubled with, but I think graphs generally can be quite tricky when it comes to kinematics. Now, we did say that the acceleration is uniform, and we said that the velocity, which is delta x by delta t, is not a constant. So this can't be a flat horizontal line. We can immediately discard that, but it is increasing at a constant rate because the acceleration is constant. So if the velocity is increasing at a constant rate, meaning uniform acceleration, then we should have a line that has a constant gradient that is a straight line. And what this means is that delta v by delta t is equal to a constant. So how do we get the values for the velocity against time if I only have a graph of displacement against time? Well, I find the gradient at every point. It's difficult to find the gradient of a line that isn't a straight line, but what I can do is draw tangents, and if I find the gradient of that tangent, what I will find is at that time, that will be the value of my velocity. At any other time, t2, I draw another tangent to that point on that curve, find the gradient of the tangent, and guess what? At that time, that will be my value for the velocity on the velocity time curve. And so this is for an object moving in uniform acceleration, and the only thing left would be to plot or sketch our graph of acceleration against time. So I hope you can see that the pattern is visible and it's evident. But obviously there's many ways we can change these problems around to sort of make the problem ever so complicated. So the acceleration is uniform, meaning the acceleration is constant. It's going to be a flat horizontal line. So a is equal to some constant, and this is equal to the rate at which velocity is changing. So the rate at which velocity changing is a constant, meaning there's one gradient for the line above, and so there'll be one value for this line. And A is positive because if I think about this carefully, the gradient of the graph of v against t is also positive. So A is positive because the gradient of v versus t is positive. The gradient of the graph above is positive. If the graph above was decreasing, then, so if I had a graph where the velocity were decreasing like that, then the gradient would always be negative. The acceleration would always be a negative value. It would be decelerating. So that's a way I could just switch things around if I would. And the value of the gradient would tell me the value of A. And so what I mean here is that the velocity is increasing. So these are some of the graphs for simple one-dimensional motions for objects that are moving in a straight line and either are stationary, moving at constant velocity, or at constant acceleration. So these graphs might not be complicated, but when the motion changes with time, it very easily becomes a situation where, yeah, these graphs can get complicated. But these are just, I'm just giving you some ideas of how to think about these graphs when you sketch them. Now, moving on from simple one-dimensional motion, which in most cases is not that complicated, to a situation where I have an object moving in 2 dimensions, which I can call two-dimensional or projectile motion. We generally deal with projectiles. So I'm going to take an example and I'm going to ask you to consider a projectile and I'm going to ask you to, like always, ignore air resistance, because air resistance would make our life a lot more difficult. But a projectile is any object that it will only be influenced by the force of gravity, and in this case it will be 2-dimensional, so it will be, we can assume it's a ball that's kicked. In fact, let's draw it. So I'm going to draw the ground, and on the ground I'm going to have maybe a football, and I'm going to kick the football such that it leaves the ground, it travels, and guess what? It's going to travel along the arc of a parabola. You know, equations of motion can tell us that, but you can try and define this for yourself. But it's going to be kicked with some initial velocity up and to the right, u, at some angle theta to the ground. So if I were to measure the angle to the ground, I'm going to get an angle theta. The mass of this ball is m, and what we will do is we'll choose, as we usually do, but again, it's completely up to you how you choose your coordinate systems, how do you choose your frames of reference. But I'm going to choose vertically upward as my positive y-axis. So anything upward is positive. And then choose anything to the right as also being positive. Like I said, like we usually do. And as the ball moves, it travels in this parabolic arc. And then at some point in time, it's going to reach its highest position. We'll call that time t equal to t1, and we'll call that height, well, we'll call it the maximum height that it reaches above the ground. This is the most simple sort of projectile motion question that you could be asked to find. Again, upward is positive and rightward is positive. Now, when the ball is in the air, whenever it's in the air, there's only one force acting on it, since we ignored air resistance. That's its weight, mg, the force due to gravity. And if this force is equal to mg, the ball's acceleration, F over m, is g from Newton's second law. So the acceleration is only that due to free fall. It's a free fall acceleration. It's a constant minus 9.81 meters per square second. Notice how I didn't say acceleration is minus g, but I said it's g, and I put the minus in front of the number. I just feel that's a better way to do things, to always have the negative in front of the value, because that specifies direction. For a vector, there's a negative sign. It simply tells us that g, or the acceleration, is downward. Kind of makes sense. When I throw something up, I expect it to come back down. I don't expect it to speed up into space. And so initially we can say t is equal to 0, and finally when the ball reaches the ground again, t is equal to t2. Now, in an ideal scenario without air resistance, the angle theta is the same for the outgoing ball as it is for the incoming ball. And the time it takes to get to the highest point is the same time it'll take to go from the highest point to the lowest point. There's a nice symmetry about this problem. But we're not going to talk about all of the complications. That would be for a problem-solving video. But initially, what do we have? Well, I kick the ball with some initial velocity u. And the problem I have here is that the ball has two components of velocity at any point in time. It's moving in an arc. It's not moving along the x-axis or along the y-axis. So what I do, like I do with vectors, is I break them into components. So the initial velocity has a y component, which I'll call uy, and a horizontal or x component, which I'll call ux. And if I look at the geometry very carefully, what I see is that the angle theta is the angle between the horizontal and the vector u. So I can label that theta, and any vector that's broken in can be broken into perpendicular components. And those are my perpendicular components, ux and uy. So with a little help from geometry, I can see that cosine theta and trigonometry, cosine theta is ux over u, which means that the horizontal component of the initial velocity ux is u cosine theta, because I have a right angle triangle that I've drawn here. And the sine of theta is uy over u, which means that uy is u sine theta. So I don't actually need to know what the horizontal and vertical components are. I can calculate them if I know the angle at which the ball is kicked and its initial velocity. And what's important to remember in this scenario is that the horizontal component of velocity doesn't change. There is no force in the horizontal direction. So as you'll learn in the topics coming up, Newton says that if there isn't a force acting on something, then the object is not going to accelerate in that direction, and its motion is going to remain unchanged. So there isn't a horizontal force acting on the ball, so its horizontal velocity remains constant. So I'll just write that down. There's no horizontal forces here. Remember, gravity is completely vertical, always points straight down. So there isn't any force with a component that's horizontal. The y component of velocity at any time, the final y component of velocity at any point in this diagram, Vy, is Uy plus G times T. So V is equal to U plus AT. We replaced V with Vy, U with Uy, and A with G. But that's how we can apply the equation of motion to find the velocity at any other point if I know what the initial speed is and I know what the time t is. So now you can see the power of using the equations of motion, the kinematic equations of motion. So even for projectile motion, even though there's two dimensions, I can break up the problem as a system of two one-dimensional motions. And then all my kinematic equations apply, and my horizontal velocity is always constant. So things work out fairly well and becomes very easy to solve, even though I may have an extra set of equations because I have two dimensions of motion. But I think the next part is something that does get a little complicated. When for two-dimensional motion, you're asked to sketch graphs of what's happening. So the first graph I'm going to sketch is the graph of displacement versus time. And I'm going to use the example that I did above, the example of the ball being kicked in a two-dimensional arc. Also, again, ignoring air resistance. So what happens if I kick the ball in a two-dimensional arc and I want to sketch a graph of displacement versus time? Again, I've chosen right as positive in both scenarios. Actually, what I'm going to do is draw two graphs for displacement versus time. One for the horizontal displacement and one for the vertical displacement. Horizontally, the ball is always moving to the right, so its horizontal displacement will always be 0. Or rather, its horizontal displacement will always be positive, sorry. And so it will be increasing, but it will be increasing at a constant rate. And so halfway through the motion, I should have drawn that better. Halfway through the motion, it will be at a time t1, half the maximum displacement, and then all the way through its journey, when it reaches the ground again, it will be its maximum distance from its starting point, t2. It will be a distance x2 from its starting point. And remember that there's constant horizontal velocity. Hence, the gradient of this graph must be a constant number. And if I were to then sketch a graph of the vertical displacement against time, the vertical displacement goes from 0 to a maximum value, back to 0 again. The ball goes up and then comes down. And the time changes. So it's actually going to be me sketching the path of the ball. So it's almost like a side-on version of me sketching the path of the ball. And its maximum height will be reached exactly when the time is equal to t1, and the height will be 0 a second time when it reaches the ground after time t2. So this is what a graph of y against t would look like. Now, why is this graph not a straight line? Because there is a force in the vertical direction. That's the gravitational force. So there is acceleration acting vertically. So there's a changing vertical velocity. Constant velocity means displacement time is a nice straight line. Changing velocity, because of the influence of acceleration, means there's a non-straight line for my displacement versus time graph. What about if I want to now plot velocity versus time? And this is where it sometimes gets calculated. Sometimes gets complicated. Should get calculated, but sometimes can get complicated when being calculated. The graph of velocity versus time. Now, I've been sketching my negative axes for the longest time, but I haven't actually used them. I'm going to be using the negative axis now. So I kick the ball with some initial velocity v, or u rather, and the ball slows down as it moves upward. And so its velocity decreases, but its velocity is positive because it's moving upwards. And I said everything that's upward is positive. But then I said everything downward is negative. So I'm only going to consider the vertical component of velocity here. But everything upward is positive and everything downward is negative. So it slows down at a constant rate, and so the gradient must be a constant value. The gradient must be negative because the velocity is up, but the acceleration is down. And so they move in opposite directions. This gradient is negative, meaning acceleration is negative because acceleration is downward. It reaches its maximum height after time t1. What happens then? The acceleration doesn't change direction, but the velocity does because it starts to move downward. And since it's now moving downward, but getting faster and faster as it moves downward, then the velocity gets bigger in the negative plane, the negative half plane. And so these are all positive values, but this half plane is all negative values. And after time t2, it reaches its maximum velocity, which is the same velocity it had when it was kicked actually, but now in the opposite direction. So velocity is initially positive, but then is negative. And what does this mean? Doesn't mean that because I'm going below the time axis, because I'm going further and further more south or further negative, that my velocity is decreasing. Velocity is a vector. So the graphs actually mean different things. And so for the top half of the graph, the speed of the ball is decreasing. For the bottom half of the graph, the speed of the ball is increasing, but it's increasing in the opposite direction. Hence, it's becoming more and more negative. And so this tells me that the velocity is increasing in the opposite direction. So the first half is for the ball moving up, and then the bottom half is for the ball moving down after it reaches its maximum height. So you can see there's a lot of things that are complicated with this graph, especially since we now have to bring in negative values. So it really is up to you to make sure that when you're thinking about velocity versus time, acceleration versus time, and displacement versus time graphs, that you remember that these quantities are all vectors. So a negative value simply is telling us, giving us an indication of what the direction is going to be, or what the direction is for that object. And the last graph that we want to sketch for this object, obviously, will be the acceleration against time. So what does the acceleration time graph look like? Another one that can get complicated. It's sometimes so complicated, so easy to mistake that it's usually put as a paper 1 question. Positive axis is upward, negative axis is downward, time is the horizontal axis. What does the acceleration do? Is it increasing? Is it decreasing? Is it wobbling? No, we did say that A is equal to G is equal to constant. If I plot a constant value on a graph, what do I get? I get a straight horizontal line. And what did I say about G? We took down to be negative, so any vector that points in the downward direction must be negative. G is no exception. It points downward, it must be negative. And so I have a straight line, always constant, that's what a constant is, irrespective of the time. So at time t1, G is minus 9.81 meters per second square. At time t2, G is minus 9.81 meters per square second. That doesn't change. So a graph of acceleration versus time, even if the object is moving in a parabola, even if it's moving in some other shape, if there's only one force acting on it, which is gravity, the acceleration will be that due to gravity, it will not change. If it would, then our entire reality would be different. And if it were positive, then as you threw the ball or kick the ball upward, it will accelerate away from you, which would be weird, because then it would get faster the further it was away from you, which we know is not true. And so an acceleration versus time graph is a straight horizontal line, and depending on what direction we've chosen as positive or negative, the graph will be either above the t-axis or below the t-axis. So you can see I wanted to spend more time in this video on sort of the graphical ideas behind kinematics. Problem solving is huge for kinematics. People have usually and typically have difficulty remembering their problem-solving techniques for kinematics when they leave it for too long. So my suggestion would be to constantly work on these graphs and on problems that have graphs in them to make sure that you don't lose that problem-solving ability. But I hope this video was helpful. Leave a like if it was, a comment down below, subscribe to the channel if you haven't already. But that's all from me, Mr. K, for now. I'll see you again next time on Everything is Relative.